Hello, my name is Jung-Suk Kim. In this video, I'd like to introduce our new paper, EquiAV Leveraging Equivariance for Audio-Visual Contrastive Learning. This is the joint work of SIIT Lab and Multimodal AI Lab in KAIST. Contrastive learning has been recently used in various fields and outperforms many other methods. Contrastive learning maximizes the similarity of the positive pair and minimizes the similarity of the negative pair. To achieve this, a positive pair and a negative pair must first be designated. For example, in the field of self-supervised learning, they usually set the positive pair as an augmented view of the original data, and other images in the batch and their augmented view are used as a negative pair. Also, contrastive learning performs well in multimodal representation learning. In this part, pair of each data becomes a positive pair, and the remaining data in the batch becomes a negative pair. For example, for an audio-visual contrastive learning, the paired audio of the visual input becomes positive data, and the rest of the audio data in the batch becomes a negative pair. However, the augmentation in a multimodal representation learning is more limited compared to single-modal representation learning. The existing premise of using augmentation assumes that the positive pairs share the same semantical meaning, which is more easily violated by augmentation in a multimodal environment. Here, we set our goal to define a high-quality representative embedding for intermodal contrastive learning. Constructing a representative embedding is crucial because the embedding of the original input data often lacks sufficient representative quality. Moreover, the embedding of the augmented data may provide incorrect supervision signals. To tackle this challenge, our approach involves aggregating embedding from multiple augmented data sources to build a representative embedding. As illustrated in the diagram, we start by creating embedding for various augmented views of the original data. This leads us to our central question: how can we efficiently obtain embeddings of multiple augmented data? The main idea behind generating multiple augmented embedding is equivariance. Equivariance is a method to train augmentation-related information for representation learning. In the diagram on the left, we start with an original input x. When this input is augmented, we get x prime, which is transformed version of x using some transformation t. Traditional invariance concept of learning aims to make fx prime equal to fx, which is effectively ignoring the transformation. On the other hand, equivariance introduces a transformation predictor u. It estimates the displacement in the latent space which corresponds to the transformation applied to the input space. So, we focus on extending and applying equivariance for audio-visual contrastive learning. If we can apply a transformation predictor in the intermodal or multimodal latent space, we can obtain the augmented embedding by utilizing only the augmentation parameter and the original embedding without including the augmented data. To achieve our goal, our method comprises three key contributions. First is architecture of transformation predictor, second is transferring intramodal equivariance to intermodal latent space, and third is drawing the representative embedding for intermodal contrastive learning. First, we propose attention-based transformation predictor architecture. The augmentation information that applied to the input space is projected with the augmentation encoder. The output of augmentation encoder is used as query, and the embedding of the original data used as key and value for multi-head attention. Through this, our model shows more accurate encoding of equivariant representations and outperforms the previous transformation predictor architecture. Second, we use shared transformation predictor in intermodal and intramodal latent space for transferring equivariance from intramodal latent space. Through this design choice, we can obtain embedding of augmented data in intermodal latent space with minimal computational cost. Third, we draw representative embedding that provide more powerful and robust supervision on audio-visual correspondence. Here, we consider expectation value of augmented embedding as representative embedding. H' is the embedding of the augmented data, and DH is the space covered in the feature space by the original data with augmentation. Then, we approximate the representative embedding as centroid of equivariant embeddings. Finally, we can compute total loss of our framework as summation of loss from equivariant intramodal space and invariant intermodal space. Also, you can check detailed loss function format in our paper. For experiments, we pre-train our model on audioset 2 million, which is a large-scale audiovisual dataset. Then, we evaluated this model on a number of downstream tasks. Here are the main quantitative results. we test our framework on various downstream tests including audiovisual event classification, zero-shot audiovisual retrieval, and action recognition tasks. As shown in the table, our method outperformed the existing state-of-the-art works, which demonstrating its effectiveness for learning rich audiovisual representation. We also conduct various ablation studies to verify the effect of each component of our framework. First of all, we investigate the impact of single-modal equivariance on multimodal representation learning. We find that the augmentation-related information learned through single-modal equivariance assists in intermodal contrastive learning. Then, we also figure out that equivariant representation can be successfully transferred from the intramodal space to the intermodal space through a shared transformation predictor. Finally, despite the inaccurate supervision from individual augmented input pairs, the centroid of these embeddings provides better supervision compared to the embeddings of the original input pairs. Furthermore, by increasing the number of equivalent representations, the centroid approaches the true mean of the augmented representations, and it consistently enhancing zero-shot retrieval and fine-tuning performance. Importantly, our method effectively balances between providing accurate supervision for audiovisual correspondence and increasing the diversity of training data. Another significant advantage of our approach is resource efficiency. For example, it increases less than 1% of computational cost and training time compared to the baseline when using 16 equivariant representations. We also explore different architecture for the transformation predictor. In the table, similarity column means cosine similarity between real augmented embedding and equivariant embedding. Compared to the simple linear layer or hypernetwork-based architecture, the proposed multi-head attention-based architecture shows higher similarity and it leading to the better performance in downstream tasks. In addition, we conduct ablation studies on training strategy, equivariant loss function, and weight scale of intramodal and intermodal contrastive loss functions. You can find the detailed analysis in our paper. For qualitative analysis, 1,000 of augmentation vectors are randomly generated for each sample, and then the equivariant embedding nearest to the centroid is selected as the substitute for the centroid. The corresponding transformation for this equivariant embedding is likely the one that best represents images for the centroid in the input space. Then, we perform the zero-shot sound source localization on the original input image and the image selected as mentioned. While the attention map on the original image is dispersed to parts beyond the main object, the attention for the augmented image, which corresponds to the substitute embedding of the centroid, is precisely and intensively concentrated on the areas that make the sound. Thank you for paying attention to our work. Please check out our paper for more information.